Hello, and let me start by saying I have given you the wonderful choice of looking at my slides using the mandatory format or myself, so I'm sorry. I'm from aviation engineering inside the Army, and the first two things you need to know about aviation engineering in the Army is as our organization is responsible for airworthiness for the Army, we effectively are the FAA for the Army. The military branches are self-certifying with regard to airworthiness. And the second thing is that when we talk about Army and aviation, we're talking about helicopters. The Army has about 4,000 helicopters. That represents by far the largest fleet of helicopters in the world. Not even Sikorsky manages fleets of helicopters anywhere close to as big as ours. And so we, in a very real sense, have the largest data sets regarding some of the most complex mechanical systems that achieve flight. And the data that we have it looks like basically three groups of data. One group of data, which is the most recent, is sensor data. And folks like UTC Aerospace Systems and Honeywell Aerospace provide us with digital acquisition systems that are on board the aircraft, capturing principally vibration is what we use to do diagnostics, but also temperature and flight parameters. Second puddle of data we have are operations. Aviation being a fairly hazardous endeavor for all involved, flight and maintenance logs are actually relatively well maintained compared to many other situations. And then finally, perhaps the most unique opportunity we have with regard to our data is a program called Rimfire, which has given us the opportunity to close the loop and label our mechanical health data. The Army takes gearboxes and engines, jet engines, and other very expensive components that are flown on the helicopters, ships them off to the depots, Corpus Christi and others, and they take them apart, and if there's something wrong with it, it flags, and we actually get a full analysis of the mechanical failure of the system. Very few people who are doing PHM actually get that piece of it, which is really nice. The opportunities, the sort of problems we're trying to solve with this data, like everyone else, we're trying to solve the mechanical health problem. We need to make sure that our aircraft are maintained in an airworthy state, and we're trying to control costs with regard to logistics. That's basically the false positive, true positive trade-off right there that we live in. And the other piece that we're trying to do is the current way we do prognostics and health calculations for our components puts a really heavy burden on the maintainers in the field who are soldiers, who are typically moved through the system in 4 to 5 years. They're not highly trained. They don't have an opportunity to become highly trained in engineering data. And so right now we put a huge amount of information in front of their eyes and try to ask them to make a decision. And a huge, significant number of times it comes back to us at Aviation Engineering. We wind up making the decision. So we're trying to codify all that information into things that will simplify decision-making for soldiers, as well as improve our accuracy in predicting the health of the gearboxes, the engines, the other mechanical systems. We launched down this path of trying to use machine learning and data science a couple of years ago. And so, if we were to start over today, we would do it very, very differently. If we were to start over 6 months ago, we would do it very differently. Both our knowledge and the state of the field moves so fast that it's very difficult. But when we dove into a particular problem, we were building a classifier. We were looking at all this huge world of what kind of models to try to use, how you tune those models. At the same time, we were trying to understand what kind of metrics you use, how you really interpret those metrics to make sure that you're not fooling yourself with the airworthiness authority. And we're going to be judging y'all when y'all come to us saying, use this model on your jet engine and fly it. And we're going to be saying whether or not you get to do that. And so we're trying to understand how we allow machine learning and data science models on board flight systems. And so we took those two things and we followed them as far as we could, and we eventually started trying to basically build this tool we call the crawler, which was to attack certain specific problems, one of which was building a classifier, a health classifier, for a nose gearbox for an Apache for AH-64. This was a pretty classic example. We put in front of the soldier something like 36 different numbers and asked them to make a decision about whether or not the gearbox is faulted. We know that these condition indicators work pretty well, but we don't have, it takes a certain amount of engineering expertise to interpret them. And then, you know, we have issues in formulating the problem because while we have a ton of data, the Army is not necessarily known for its incredible adherence to policies, and so we only get about 50 to 70% of the data in the field back at the top tier at the fleet level. And then, of course, mechanical health data is incredibly skewed. I'm not really even going to go into the rest of this. There's no time in these really fast presentations. There's much more details in the paper on this one. This one is a little bit easier to present in this format. This was a second application that we used our little crawler for. In this case, one of the engineers in our unit basically came to us and said, hey, there's this new kind of sensor fault that we're seeing on accelerometers. It's on a new model, and we've never seen anything quite like it before. We don't really have a mathematical model for why. We don't have a physical or mathematical model, but we have a bunch of examples. And so this was an excellent opportunity for us to try to exploit the data science toolkit and see if we could, you know, do something useful. And what we did was, let me explain briefly. These are 3 different spectra of vibration as recorded by our HUMS box. The bottom one is a normal sensor. The sensor itself is healthy, reporting whatever information about vibrations going on. The top one is a fairly classic sensor fault that we know and understand. In the frequency domain like this, it's referred to in the field as the ski slope fault. It represents typically a loose wire, a DC offset in the signal processing chain. That middle one is weird and new, and we called it the dirt bike slope because we didn't know what else to call it. And we went through a process of a fairly manual process that probably would have been better done with online learning. But we went through a fairly manual process of we labeled a small number of cases, trained some classifiers, which I then took the top 5 out of this huge set that I'd trained and used that to identify new cases. And we did that multiple times. And in particular, we identified several new examples of the failure that were happening in the fleet that we didn't know about previously, because we get, you know, we have 700 of these aircraft, and we get reams of this data every week. I'll just leave it there, and I'll say that in our experiments thus far, these techniques, machine learning and data science, are helping us reduce soldier burden by this process of taking complex engineering knowledge and codifying it into a model that we can put out in the field and red light, green light, do you fly today? It's making our engineering tasks a whole lot faster, especially these data search tasks where we know that this kind of thing happens, but we have 3 terabytes of sensor data to dig through. And believe it or not, this is something that last year would have been done manually by engineers individually looking at spectrum by spectrum. And the last point is help. We are new to this. I by no means think that we are very sophisticated yet. But we have some really interesting data sets, and we're trying to find ways to exploit them. And we also have this unusual mandate of needing to be able to certify data-driven models to go on flight systems. And bluntly, the problem of overfitting terrifies us. The problem that people can convince themselves that the model works really well, but it doesn't. You put it on an aircraft and the aircraft crashes. Aerospace is a very conservative, you know, very conservative field. And so we're trying to get out ahead of this and be able to understand and provide guidance to our vendors of ways that we can get past that and actually be able to certify and field these systems. That's what I have.